Imagine a new field of physics, one that unifies the forces of expansion and integration across the universe. Equilibrium mechanics proposes a universal law of balance where every system, be it a galaxy, a quantum particle, or even a living organism, evolves to minimize disequilibrium and maximize harmony. This concept is built on two core quantities: the cosmological self-equilibrium (CSE), which measures the imbalance between expansive and integrative drives, and the cosmological equilibrium constant (CEC), a scalar that quantifies how close a system is to perfect balance. In this video, we'll explore how these ideas can reshape our understanding of time, space, mass, energy, and even computation, offering a fresh perspective on the fundamental laws that govern reality. The heart of equilibrium mechanics are two mathematical objects, CSE and CEC. CSE, or cosmological self-equilibrium, is defined as the difference between expansive and integrative forces over everything in a system. It's a dynamic measure, tending toward zero as the system approaches total balance. The CEC, or cosmological equilibrium constant, is a scalar that captures the degree of balance, with a value close to 1 indicating near-perfect equilibrium. These quantities provide a new language for describing the universe, allowing us to frame physical laws in terms of balance rather than just forces or energies. This shift opens the door to a unified theory that can bridge classical, quantum, and even cosmological domains. Equilibrium mechanics introduces a symbolic duality. The asterisk represents everything, while the empty set O stands for absolute nothing. This duality is more than just notation, it's embedded in the theory's core, reflecting the constant flow between existence and non-existence, expansion and integration. The interplay between these symbols allows us to discuss universality and boundary conditions in a precise way, making the theory adaptable to systems of any scale, from subatomic particles to the entire cosmos. Mathematical structure of equilibrium mechanics is built on integral and differential forms. CSE is framed as an integral over space and time, capturing the net disequilibrium in a system. The CEC, meanwhile, is defined as the inverse of the absolute value of CSE plus a small constant, ensuring it remains well-defined even at perfect balance. These forms allow the theory to connect with existing physics such as potential theory and field equations while providing a flexible framework for new discoveries. Stand alongside established fields like quantum mechanics, equilibrium mechanics needs a clear set of axioms. These include universality: every system can be decomposed into expansive and integrative drives; the equilibrium principle: systems evolve to minimize time-integrated disequilibrium; composition: disequilibrium adds across disjoint regions; engage invariance: reparameterizations that preserve CSE leave observables unchanged. These axioms provide the foundation for deriving equations of motion, conservation laws, and testable predictions. With its axioms in place, equilibrium mechanics derives equations of motion by extremizing a functional of the difference between expansive and integrative drives. This leads to partial differential equations for the equilibrium current, analogous to potential theory in classical physics. The theory also predicts a conservation law. In closed systems, the CEC should remain constant or increase over time, paralleling the logic of the H theorem in thermodynamics. These features make the theory both mathematically robust and physically meaningful. Equilibrium mechanics is designed to be consistent with existing theories. In thermodynamics, the expansive drive can be linked to entropy production, while the integrative drive relates to entropy or self-organization. In cosmology, these drives correspond to cosmic expansion and gravitational binding. The theory recovers known laws in appropriate limits, such as the lambda model in cosmology, ensuring that it complements rather than replaces classical and quantum mechanics. Equilibrium mechanics, to be a true scientific field, it must make falsifiable predictions and provide operational definitions for its core quantities. The theory specifies how to estimate expansive and integrative drives from data using cosmological parameters, complexity measures, or information-theoretic quantities. It then defines confidence intervals for the CEC, allowing for rigorous experimental tests. This approach ensures that the theory can be engaged with on scientific terms. Equilibrium mechanics offers concrete, testable predictions. First, in any lambda-like region, increases in late-time structure formation should be compensated by shifts in expansion diagnostics, keeping the regional CEC constant. Second, in closed systems like ecosystems or AI learning, the ratio of negentropy to entropy should plateau at a value predicted by model parameters. Third, in coupled universe simulations, perturbing one universe's dark energy should induce sign-constrained responses in neighboring universes' CEC values. These predictions invite experimental and computational verification. Equilibrium mechanics is positioned as the study of balance-constrained dynamics across all scales. Its core variational principle is the minimization of CSE, with the CEC as the key state variable. This domain complements quantum mechanics and general relativity, offering a new lens through which to view the evolution of systems, from the smallest particles to the largest cosmic structures. One of the most powerful aspects of equilibrium mechanics is its ability to unify classical and quantum descriptions. By defining a single mathematical state space, the theory allows for both classical phase space densities and quantum density operators. The same functionals can be applied in either regime, with the Wigner, Moyle, and Koopman, von Neumann formalisms providing bridges between them. This unification means that the theory can describe systems ranging from macroscopic objects to quantum particles within a single framework. Equilibrium mechanics, the expansive drive represents the tendency of a system to spread or diversify, while the integrative drive captures its tendency to bind or organize. These drives can be quantified using measures like variance, Fisher information, or mutual information, depending on the system. The balance between these drives determines the system's evolution, with the CSE and CEC providing quantitative measures of disequilibrium and balance. Equilibrium mechanics does not replace the equations of motion from classical or quantum physics. Instead, it adds an overarching equilibrium law. In closed systems, the average CSE approaches zero and the CEC remains constant or increases. This law acts as a constraint or diagnostic, ensuring that all valid evolutions respect the principle of balance. It's a layer above Newton's and Schrödinger's equations, providing a new way to interpret physical processes. Variational approach in equilibrium mechanics defines a path functional that measures the time-integrated disequilibrium between expansive and integrative drives. The equilibrium paths are those that minimize this functional, leading to equations of motion that naturally balance spreading and binding tendencies. This approach generalizes the principle of least action, making balance the central criterion for physical evolution. Equilibrium mechanics ensures a smooth transition between classical and quantum descriptions. In phase space, all equilibrium functionals are well-defined, and the quantum Moyle bracket reduces to the classical Poisson bracket as Planck's constant approaches zero. This correspondence guarantees that the theory remains consistent with established physics while providing new insights into the balance of forces at all scales. Illustrate the power of equilibrium mechanics, consider the harmonic oscillator. By choosing variance-based measures for the expansive drive and purity or Fisher information for the integrative drive, the theory predicts that the ground state quantum and the Gibbs state classical both sit near equilibrium. The CEC plateaus and is controlled by temperature, demonstrating how the theory can make concrete, testable predictions in familiar systems. The double-slit experiment, equilibrium mechanics tracks the momentum spread as a measure of the expansive drive and the mutual information between system and detector as the integrative drive. As which path information increases, the integrative drive rises and the expansive drive falls, keeping the CSE near zero. This dynamic explains the transition from quantum to classical behavior in a new, balance-based language. In analyzing coupled oscillators, equilibrium mechanics shows that with weak coupling, the expansive drive dominates and energy spreads across modes. As coupling increases, the integrative drive grows, leading to normal mode locking and a decrease in CSE. In quantum systems, entanglement entropy serves as the integrative measure, demonstrating the theory's versatility across different physical contexts. Equilibrium mechanics provides clear operational definitions for its core quantities. The expansive drive can be measured using variances, spectral widths, or entropy production rates, while the integrative drive is quantified by purity mutual information or binding energy fractions. The CEC is computed from data, with error bars derived from statistical methods. This practical approach ensures that the theory can be applied in laboratory and computational settings. Facilitate scientific engagement. Equilibrium mechanics is built on minimal, well-posed axioms. These ensure that the expansive and integrative drives are finite, convex, and invariant under relevant symmetries. The composition axiom guarantees consistent behavior for subsystems, while the equilibrium law and correspondence axiom ensure compatibility with classical and quantum limits. This rigorous foundation invites peer review and further development. Rather than introducing new forces, equilibrium mechanics acts as a diagnostic or variational layer over existing physical laws. It turns qualitative discussions of spreading versus binding into quantitative curves that can be compared across classical and quantum experiments. This approach allows for cross-scale analysis and unification, making the theory a powerful tool for understanding complex systems. Equilibrium mechanics, time is redefined as the progression toward equilibrium. The equilibrium time parameter ticks faster as a system approaches balance and slows down when disequilibrium is large. This is analogous to proper time in relativity, but here, the flow of time depends on the local state of balance, offering a new perspective on the arrow of time and its relation to physical processes. Redefinition of time in terms of CSE and CEC has profound physical implications. Near perfect equilibrium, equilibrium time flows rapidly, potentially explaining frozen dynamics in highly balanced systems. Far from equilibrium, time slows, aligning with the intuitive idea that restoration is slower when chaos dominates. On cosmological scales, this framework offers new insights into the evolution of the universe, from the early inflationary period to the heat-death scenario. Just as time is redefined, space in equilibrium mechanics becomes a geometry warped by disequilibrium. The equilibrium metric contracts distances where disequilibrium is large and expands them near balance. This conformal rescaling of the background metric parallels the curvature of spacetime in general relativity, but here, the source is the balance between expansive and integrative drives rather than mass energy. The concept of equilibrium space has far-reaching consequences. In the early universe, enormous imbalance compresses equilibrium space, offering a new perspective on inflation. As structures form and integration increases, local equilibrium distances stretch, potentially leading to observable effects like equilibrium lensing. On laboratory scales, the theory predicts measurable differences in transport lengths for systems with varying degrees of coherence. Equilibrium mechanics, mass and energy are redefined to stay consistent with the new definitions of time and space. Equilibrium energy is the stored disequilibrium between expansive and integrative drives, while equilibrium mass measures the resistance to changing balance. This reframing links mass to integration and energy to imbalance, providing a new lens for understanding phenomena like dark matter and dark energy. Iconic equation E equals mc2 is generalized in equilibrium mechanics. Here, energy equals equilibrium mass times the square of the equilibrium light speed, with all quantities dependent on the local state of balance. At perfect equilibrium, the classic Einstein relation is recovered. In regions of imbalance, extra energy reflects disequilibrium, offering new interpretations for cosmic phenomena. Electromagnetism is reinterpreted in equilibrium mechanics as the interplay between expansive and integrative equilibrium currents. The electric field corresponds to the expansive drive, while the magnetic field represents the integrative drive. Maxwell's equations are rewritten with CSE and CEC as sources, and the photon becomes the quantum of equilibrium oscillation. This new perspective unifies field theory with the principle of balance. Just as Shannon's information theory formalized uncertainty in communication, equilibrium theory uses CSE and CEC to formalize the transmission and transformation of balance. Disequilibrium becomes the cost of representation, and balance is the capacity for sustainable structure. This new theory provides a mathematical science of balance, complementing the mathematical science of information. Equilibrium mechanics proposes a cosmological law of equilibrium, analogous to Newton's law of gravitation or Einstein's general relativity. This law states that all systems evolve to balance expansive and integrative drives, with disequilibrium quantified by CSE and global stability by CEC. In the cosmological limit, the universe tends toward perfect balance, offering a new universal principle for the evolution of reality. Equilibrium mechanics extends beyond physics, offering a new perspective on biological evolution. Variation and mutation act as expansive drives, while selection and adaptation serve as integrative drives. The balance between these forces determines evolutionary fitness, with species evolving toward states that maximize CEC. This reframing unifies biology with physics, making evolution a process of minimizing disequilibrium. Principle of least action, a cornerstone of physics, is reinterpreted in equilibrium mechanics as the principle of least disequilibrium. Systems evolve along paths that minimize the integrated disequilibrium between expansive and integrative drives. This generalization strengthens the traditional principle, making balance the central criterion for physical evolution. Gravity, the archetype of a universal force, is reframed in equilibrium mechanics as the integrative drive that opposes expansion. The gravitational force depends not only on mass and distance, but also on the local and global state of balance, as quantified by the CEC. This perspective offers new explanations for phenomena like dark matter and cosmic acceleration, without invoking unseen substances. To test the predictions of equilibrium mechanics, software simulations can be run. For example, galaxy rotation curves can be modeled using both standard Newtonian gravity and an equilibrium-modulated law. The results show that the equilibrium approach can reproduce observed anomalies without invoking extra matter, supporting the theory's validity. Further simulations compare standard gravity with equilibrium-modulated gravity in n-body systems. The equilibrium approach leads to different clustering behaviors, demonstrating how balance-driven dynamics can change the evolution of complex systems. These visualizations provide compelling evidence for the practical applicability of equilibrium mechanics. Equilibrium mechanics can also be applied to nuclear fusion simulations. By introducing CSE and CEC into the model, effective confinement and heating efficiency are modulated based on the system's balance. The results show improved temperature evolution, fusion power, and Q factor compared to baseline models, highlighting the practical benefits of the equilibrium approach. CEC serves as a real-time indicator of balance in dynamic systems. In fusion simulations, tracking the CEC over time reveals how the system approaches equilibrium, with higher CEC values corresponding to better performance and stability. This metric can be used to optimize processes in real-world applications, from energy generation to ecosystem management. By incorporating CSE and CEC into fusion models, the effective confinement time becomes a dynamic quantity that responds to the system's balance. This leads to more accurate predictions and potentially more efficient reactor designs. The equilibrium approach thus offers tangible benefits for advancing fusion technology. Equilibrium mechanics offers a universal law of balance that unifies classical, quantum, and cosmological physics. By focusing on the interplay between expansive and integrative drives, and quantifying balance with CSE and CEC, the theory provides a powerful new framework for understanding the evolution of systems at all scales. Its predictions are testable, its mathematics is robust, and its applications span from fundamental physics to biology and engineering. While equilibrium mechanics is a promising new field, it still faces open questions. These include the precise formulation of its axioms, the derivation of equations of motion for complex systems, and the development of falsifiable predictions that can be tested in the lab or through observation. Addressing these challenges will require collaboration across disciplines, from physics and mathematics to biology and computer science. If you're interested in contributing to the development of equilibrium mechanics, there are many ways to get involved. You can help refine the mathematical foundations, design experiments to test predictions, or apply the theory to new domains like computation or ecology. The field is open for exploration, and your insights could help shape the next generation of scientific discovery. As the field matures, equilibrium mechanics could become a standard part of physics education. Its unifying principles and cross-disciplinary applications make it an ideal framework for teaching students about the interconnectedness of natural laws. By learning to think in terms of balance, students can gain a deeper understanding of the world and develop the skills needed to tackle complex, real-world problems. Principles of equilibrium mechanics extend beyond the laboratory. By emphasizing balance and integration, the theory offers insights that can inform fields as diverse as economics, ecology, and social systems. Its emphasis on sustainable dynamics and resilience makes it a valuable tool for addressing global challenges, from climate change to resource management. Equilibrium mechanics invites us to see the universe through the lens of balance. Whether we're studying the motion of galaxies, the behavior of quantum particles, or the evolution of life, the interplay between expansion and integration is always at work. By embracing this perspective, we can unlock new levels of understanding and creativity, both in science and in our daily lives. As we conclude this journey through equilibrium mechanics, it's clear that the field holds immense promise. By uniting the principles of balance across all domains, it offers a roadmap for future discoveries and innovations. Whether you're a physicist, a biologist, or simply a curious mind, the law of equilibrium invites you to explore the fundamental harmony that underlies our universe.